Hi girls, this lesson is going over graphs of logarithmic functions. Okay, so first we're considering the exponential graph, y equals a to the x. If a is between 0 and 1, so it's like a half or a third or 2/5, then the function looks like this one here going downwards from left to right. But if a is bigger than 1, so 2 or 10, the function's going upwards, like that. So, now, we've discussed this before, but if fx equals a to the x, then the inverse of the function is log base a to the of x. So, the logarithmic graph is just the reflection of the exponential graph through the line y equals x. So, for instance here was our original y equals a to the x. If you reflect that along the line y equals x, you end up with this one here, the green one, which is the inverse. So that there is y equals log to the log of x base a, where a is between 0 and 1, so it's like a half or something like that. On the other side, here's y equals a to the x. And so if we again reflect that along the line y equals x, which is that one, we get the graph of the logarithmic function, which is there. This is the one we look at more commonly when a is bigger than 1. Now, a couple things to notice on this graph. First of all, the x-intercept is 1. This is because when y is 0, it's log of 1 that equals 0. So that's x there and that's y. So log of 1 is 0 because remember, anything to the power of 0 is 1. So transforming that into a logarithmic function, it means log of 1 equals 0 no matter what the base is. So that's why for both graphs actually, the x-intercept is always 1. And then it's worth noting that the y-axis is like an asymptote. We never quite get there. This is because log of 0 doesn't actually exist. You could put it into your calculator and you would get undefined because remember, you can't have any power of a number that equals 0. So like 2 to the power of 0.01, that's not going to equal 0. There's nothing that you could put 2 to the power of to make it equal 0. And that's why we never actually hit the y-axis. And also, you could never put, say, 2 to the power of something to get a negative number. And that's why the log function, so in this case, the red function here, doesn't exist on this side where x is negative. So for both of them, the log function doesn't exist on the y-axis and when x is negative because you can check on your calculator as well, you can't find log of 0 or log of a negative number. So here's a summary again. Both have domain x is bigger than 0 because we can only find the logs of positive numbers. Both have a range of all real y, so we go up towards infinity and down towards infinity for both of them. Both graphs have a vertical asymptote at x equals 0, or in other words, at the y-axis. To find the domain of log of a function, we just put whatever's in there in that function bigger than 0 and solve it. So for instance, if I've got log of, say, 2x plus 3, to find the domain, this part in here has to always be bigger than 0. So I would do 2x plus 3 bigger than 0, solve it, minus 3 to both sides, divide by 2. X is bigger than negative 3 on 2, so that would be the domain. For a is between 0 and 1, like a half or a third. As x approaches infinity, y approaches negative infinity. What am I talking about here? Okay, so as x approaches infinity, so x is getting bigger, y is going downwards. So that's why it's approaching negative infinity. As x approaches 0, so goes backwards like this, y approaches positive infinity. for a is bigger than 1, as x approaches infinity, y approaches positive infinity, so it's going upwards. And as x approaches 0, y approaches negative infinity. And girls, those last 2 points, you don't necessarily have to remember them. If you were trying to graph a function, you might just sub in a couple points and then recognize the shape. So consider fx equals log of x plus 1 base 3 minus 2. Find the domain and range of f. Okay. So, the domain, basically the only rule we have is that the inside function has to be bigger than 0. Therefore, for the domain, x plus 1 must be bigger than 0. If I minus 1 on both sides, x must be bigger than negative 1. So that there is the domain. The range is all real y, as it is for all log functions. Find any asymptotes and xy intercepts. Okay, so to find the x-intercept, we want y to be equal to 0. So that would mean log base 3 of x plus 1 minus 2 equals 0. So what I could do there is move the 2 over, so I get log base 3 of x plus 1 equals 2. Put both sides to the power of 3 because I'm trying to cancel out the 3 and the log 3. So that becomes x plus 1 equals 3 to the power of 2, which is 9, minus 1 minus 1, x equals 8. So my x-intercept is x equals 8. Now when x is 0, for the y-intercept, I get y equals log base 3 of 1 minus 2. Now hopefully you remember log of 1 is always 0, so I get 0 minus 2, which is negative 2. So that there is the y-intercept. So I can start graphing these already. So I've got 8 as the x-intercept and negative 2 as the y-intercept. Now, what about an asymptote? Well, x plus 1 can never equal 0 because we can't find the log of 0. So, for the asymptote, and I should say vertical, x plus 1 would equal 0 because that is when a log is undefined. Log of 0 is undefined. Okay, so I minus 1 on both sides, x equals negative 1. So that there is the asymptote. And girls, remember it's important when you're being asked for an asymptote, you have to give it as an equation. X equals negative 1. If you say just negative 1, I don't know if you mean y equals negative 1 or x equals negative 1. So let's draw in that asymptote at x equals negative 1. So I should use a ruler. And to draw an asymptote, we should draw it with dashed lines to show that it is the asymptote and not the actual function that we're trying to draw. And we should label it as x equals negative 1. Okay, so now we're pretty much ready to draw it, but let's keep answering the questions. It now says, C, sketch the graph of f showing all important features. The important features really are the shape, the asymptotes, and the intercepts. So we can see that it should pass through the 2 blue crosses and approach the asymptote like that. Okay, nice sketch and doing that shape. So that's the kind of shape we want. And I should label it. I can just say y equals fx or y equals log x plus 1 base 3 minus 2. Either one. Now, it's important to note, why does this look different from the ones we had before? It makes sense that if we look at this function, the fact that it's x plus 1 means we shift to the left 1 unit, and minus 2 means we shift down 2 units. So for instance, previously, this log function would have had an x-intercept at 0, 1 here. But that's moved down 2 units and across and left 1. So it's moved 1, 2 down and left 1. So that's why we have a y-intercept at -2. That's where it's moved to. So I just wanted you to appreciate our transformations that are happening here, which is why it looks the way it looks. So it goes with everything else we've done with transformations. Okay, find the inverse and explain how to verify your answer. Okay, so part D. To find the inverse, we swap the x and y, so it becomes x equals log base 3, y plus 1 minus 2. Now, to get the y as a subject, first I need to add 2 to both sides. And then because this side here is just log of something, I can put it to the power of 3 to cancel out the log. So by putting both sides to the power of 3, so I put this side to the power of 3 and also all of this. So like the left-hand side becomes 3 to the x plus 2. On this side, the 3 and the log 3 cancel out. So I get 3 to the x plus 2 equals y plus 1. Then minus 1, cancel, cancel, and I get y equals 3 to the x plus 2 minus 1, or if you like to use our notation, f inverse x equals 3 to the x plus 2 minus 1. To verify our answer, there's a few things we can do. We can show that the inverse and the original function cancel each other out. Or we can show that the asymptote actually gets reflected around about the line y equals x. And we can show the domain and range swap. So I'm going to show you a few ways to verify your answer. Basically, our original asymptote of our function was x equals -1. So if that gets flipped about the line y equals x, which would be this line here, basically it should end up as the line y equals -1. So it would be flipped into this one here. You don't have to draw that, I'm just explaining it. So if we look at our function, I might just move over here. Here's our inverse function. Now, all inverses have so if it was just 3 to the x plus 2, the asymptote would be the x-axis, because it would approach the x-axis like that. But because I'm getting shifted down by -1, this is going to shift down to -1, so the asymptote will be there. So the asymptote for the inverse function is y equals -1, which is which is horizontal, and it is the flip of the line x equals -1. So this is the reflection of the original asymptote of x equals -1. Oh, sorry, I should say about the line y equals x. Because remember, for something to be its inverse, all the properties of it have to be reflected about the line y equals x. So if that happens, then we know it's correct. Also, let's now find the domain and range of the inverse function. So the domain is all x. Any value of x could be put in that power. There's no problem at all. Any number at all could be done. So the domain, so I might write for f inverse. The domain is all real x, and the range is, now remember, a normal inverse function would be y is bigger than 0, like here, but because we're shifting it down 1, it's y is bigger than -1. Now, look at those and compare it with the original domain and range. Basically, the x and y have just switched roles, and for that reason, we know it's the inverse function. So basically, we can write, since we can say here this is the opposite of the original function, therefore, or maybe in brackets write x and y have just swapped roles. Therefore, it is the inverse function. It might also be, another way to write that is that, say the domain is all real x, you can just say this equals the range of f, and this equals the domain of f. So therefore, it's the inverse function. That's another way to write it. So basically, to verify that our function was the inverse, we showed that the asymptote got reflected about the line y equals x, and that the domain and range just switched. Okay, so one more question. Consider fx equals e to the x minus 2. Find its inverse. Okay, so we switch, remember fx is just like y. So we switch x and y and get x equals e to the y minus 2. Now how do we get rid of the e? Opposite of e is ln, so I find the ln of both sides and get ln x equals, the ln and the e cancel out, and I get y minus 2. Add 2 to both sides, and I get y equals ln x plus 2. Make sure it doesn't look like the plus 2 is inside the log. So we probably should write it with the inverse notation. F inverse x is ln x plus 2. Sketch f and f inverse on the same axes. Okay, so let's do f first. F is just e to the x minus 2. So what are some things we can do? When x is 2, we're going to get 2 minus 2 is 0, e to the 0 is 1. So hopefully you realize that the point 2, 1 lies on the axis, the exponential curve. Also, we know the basic function is increasing. When x is 0, you get e to the negative 2. Sorry, I should be writing this out. So for b, so I subbed in 2. When x is 2, I got y equals e to the 2 minus 2, which is e to the 0, which is 1. So therefore we know the point 2, 1 lies on it, which we've graphed. When x is 0, we get y equals e to the negative 2. Now if you put that on your calculator, you get 0.135. So something very small, so that's the y-intercept, which is like down here somewhere. Also, when y is 0, that's actually never going to happen because the exponential curve is always above 0. So I think we can see clearly that the curve will look something like, like this. Keep it very low on this side. slowly go up. If you want, you can sub in, say, 4 or 3 to estimate the value, but it should just slowly go up like that. So that's y equals e to the x minus 2. Now, the inverse, let's just draw it from scratch and then check that it is the reflection along the line y equals x. So here's the inverse there. When x is 0, we actually don't get a value because you can try and put in your calculator, ln of 0 is undefined. So our asymptote will be the y-axis again. When x is 1, ln of 1 is 0 plus 2 is 2. So we get this point here. So when x is 1, 0 plus 2. So we get the 0.12 on there. And that makes sense because it's reflected along the line y equals x. And then when you can sub in now another point, say when x is 2, if you put that in your calculator, ln 2 plus 2, make sure the plus 2 bit is outside the log, and you get about 2.6, so that is somewhere here. And now if you wanted, you could put in, like, for instance, a half, if that helps. So like ln a half plus 2. If you put that in your calculator, you get 1.3, so we're somewhere down here now. So we can see the shape is like this, somewhere like that. I think I'm going a bit too downwards at the end there. Should be more like that. Okay. So that's just using a few points, putting them in. Now, let's graph the line y equals x and see if it looks like they're the reflection of each other. We weren't asked to do this, but it's worth just having a look to verify the way it should be. So here's the line y equals x. As you can see, my graph isn't perfect. We would go a bit off here. So I'm guessing I should have drawn it a bit more like this. A little bit more up. And that would be a bit better. Okay, but you get the idea that even just by subbing in points, we do get two graphs that are reflected along the line y equals x as they should be because they're inverses of each other. State the domain and range of both functions. Okay, so now let's just focus on f. Okay, and this is part C. The domain for f, so that's the black one. It actually crosses all x values, so we can say all real x. The range is only larger than 0, so it's above the x-axis, so it's just y is bigger than 0. Now, for the inverse function, the blue function, the domain is just when x is bigger than 0, and the range covers all real y. And again, hopefully you can see that for f and f inverse, the domain and range have just swapped, as they should since they're inverses of each other. Find any asymptotes and intercepts of the functions. Okay, so for y equals the original function, so for y equals e to the x minus 2, the intercepts, basically we found before the y-intercept is y equals 0.135. And the asymptote, there's a horizontal asymptote for the black one. At y equals 0, or in other words, the x-axis. I'm talking here, the green green line here, which is where y equals 0. So for the black curve, that green asymptote goes with that. For the inverse, which was again, let me see, ln x plus 2, or you could just say the f to the negative 1. What have we got? We've got an x-intercept. Now, it should just be 0.135, but let's double check by making y equal to 0. So we get 0 equals, and remember we're doing y equals 0 for the x-intercept, ln x plus 2. Now, to work that out, to solve it, remember you could actually use nsolve in your calculator to solve that for you, or to do it by hand, we would need to minus 2 on both sides, so we get negative 2 equals ln x, because once the ln x is by itself, I can put each side to the power of e, cancel the ln, and get x equals e to the negative 2, and if you put that in your calculator, again you get 0.135, which corresponds to the y-intercept of the inverse of it. So it makes sense that we got the same value there. So that's the x-intercept. It didn't have a y-intercept, so we don't need to find that. Now this one has the blue function has a vertical asymptote. And that's just the line x equals 0, or in other words, the y-axis. Remember, that's this line here. For the blue function, that's the asymptote, and that's the line x equals 0. And that's it. Now, what I would like you to do before you start working on the exercise 4G, I would like you to actually do B and D using your calculator. So, I'd like you to open a graphs page on your calculator. Make sure you can sketch both the functions fx equals e to the x minus 2 and the inverse function ln x plus 2. So make sure you're able to put them into your calculator and graph them. And also I'd like you to look at D on your calculator. Make sure you can find the x and y intercepts using analyze graph on your calculator. And also see if you can identify the asymptotes from your calculator. I've actually got a part in functions of my iBook that's on how to find asymptotes on a calculator that you might want to look at as well. So I'd like you to just practice your calculator skills there and then work on exercise 4G. Thank you, girls.